episode. It's been a while since I've made any video notes and almost kind of forgot how. Obviously, tonight I'm going to be talking about circular motion, and I'm going to begin with talking about centripetal acceleration. Typically, we talk about force before acceleration, but I think this makes more sense to talk about centripetal acceleration first. It's a little bit of a weirder topic, I think. Here's a quick recap on Newton's first two laws, which are why we have centripetal acceleration. If we have an outside force, we will have a change in an object's velocity. And when we have this outside force, we will have an acceleration. Now this acceleration is a vector, and this acceleration vector can be broken down into two components, one that's parallel to the object's motion, and then one that's perpendicular to the object's motion. Up until now, we've been dealing with parallel to the motion. The centripetal acceleration is perpendicular to the object's motion. As you know, acceleration is a change in velocity, whether that be speed or direction. And what we're going to be focusing on tonight is this change in velocity in terms of direction, and that's why what we have with uniform circular motion. And what we're going to take a look at, and you probably know this, that the direction of the acceleration, which is the same direction as the change in velocity, is inward. It's towards the center of the circle, hence centripetal acceleration, which means center seeking. I'm going to take a quick look as to why that is, and that's almost the purpose of this discussion tonight. So let's take a look at an object. It's going around a curve, so to speak, I guess, and from point A to point B we have two different velocity vectors, same magnitude, different direction, and they're all the same, both the same distance from some center point, and we'll call that distance r, which stands for radius. So we have a final velocity vector, and if we take our final velocity vector minus initial velocity, we have a change in velocity. Acceleration is related to the change in velocity, and it's in the same direction as change in velocity. And kind of looks pretty decent with my picture, but it's not perfect. But this change in velocity vector is pointing right there in the center of that turning radius. If we look at the arc length from A to B, it's through some angle, what I call delta theta. And this angle is, and the arc length is how we are able to derive the centripetal acceleration expression, which is what I want to take a quick look at. It's kind of a neat derivation. Not necessarily important to know, but it's just kind of neat to see where that centripetal acceleration formula came from. And it comes from velocity is change in displacement over time. Kind of the kicker here, this change in displacement is an arc length. And so that's where this trig or geometry or whatever those math skills that you've gotten come into play. S is the arc length between A and B. When we're dealing with a circle, the arc length is the radius times the angle. So going back to our picture, it's this angle right here. This is the arc length from A to B. And that angle is measured in radians, not degrees. And so when you do the calculation, it has to be done in radians. It's somewhat of a confusing thing. So if we plug in r delta theta for my arc length, we have the velocity as r delta theta over delta t. And then we could rearrange for our change in time, and we have, there you go, r delta theta over v. Now, acceleration is delta v over delta t. And that's nothing very big and exciting. This expression right here, though, is kind of new. Delta v, the change in velocity, is the velocity times the angle that it went through. Again, this goes back into, there's our change in velocity. This angle right there is theta. And so that's a geometry expression. This delta v is v delta theta. But when we substitute it in for acceleration, and then if we substitute in, so when we substitute that in for acceleration, and we substitute t in, and now it's getting kind of messy, we do a bunch of, a little bit of simplifying, and we get our centripetal acceleration expression, tangential velocity squared over r. Okay. I mentioned earlier that the acceleration vector can be broken up into one that's parallel to the object's direction of travel. And in this case, we're going to call it the tangential acceleration. It's related to the tangential velocity. The tangential acceleration will occur if the speed increases or decreases. So the tangential velocity, it basically goes faster or slower around the curve. It's tangent to the circle, hence tangential acceleration. This is kind of the, for lack of a better way of saying it, the normal acceleration vector that you're used to working with. So if we have a car traveling in a circle, the tangential acceleration will cause the car to either speed up or slow down. Okay. The other acceleration is perpendicular to the direction of travel, which is the centripetal acceleration. This occurs if the object's velocity direction changes, and as we just saw, it's directed towards the center of the path. So kind of recapping here, car traveling in a circle, the centripetal acceleration, it's actually the result of the centripetal force, which we're going to talk about in just a second. And while this force is present, so is centripetal acceleration. While the centripetal acceleration is present, the car is going to be turning. In a sense, tangential acceleration is how fast the car is speeding up or slowing down. Centripetal acceleration is kind of how fast the car is turning. The centripetal acceleration is actually a little bit of a weird term. It has units of meters per second squared, but it's based on a turning speed and not necessarily increasing or decreasing velocity. I've always felt that was a little confusing with centripetal acceleration, and don't get really too excited by it, except for the fact that it leads us into centripetal force, which will be our next topic area. So, like I said, a little bit out of practice. Hope it wasn't hideous.